So in this torsion topic, we are discussing how to design a shaft or how to design a member which is subjected to, carrying a power from one point to another point. Okay, how to design a member which is subjected to torque. More specifically, what is the difference between torque and force? You may heard about torque or twisting moment. What is the difference between torque and force?
Torque is a force acting at a distance from a point versus torque is a force acting at a point. Rotating a torque.
Yeah, yes. So that is torque. Actually, we use the term torque where we come with a rotating force, or if you want to rotate a member, we applying torque, a twisting moment. Okay, a twisting moment or torque. Torque is nothing but it is a rotating force. Okay, so we apply a rotating force or this twisting moment to rotate a body. Okay, so torque or twisting moment is a measure of the turning force or rotating force on an object such as bolt or flywheel. For example, in this case, see this window. See this window. This window open ആയിട്ടുള്ള window close ചെയ്യുമ്പോൾ നമ്മൾ എവിടെ പിടിച്ചാണ് rotate ചെയ്യേണ്ടത്? ഈ എൻഡിലാണോ അതോ ഈ എൻഡിലാണോ? ഏറ്റവും extreme എൻഡിലാണ് അല്ലേ? So to rotate this window, we have to apply force at this point, at this extreme end. അല്ലേ? എക്സ്ട്രീം എൻഡിൽ ലോഡ് അപ്ലൈ ചെയ്തതിൽ എന്നാ പ്രോബ്ലം? ഫോർ എക്സാമ്പിൾ ഹിഞ്ചിന്റെ അടുത്താണ് നമ്മൾ ഫോഴ്സ് അപ്ലൈ ചെയ്യുന്നതെങ്കിൽ എന്താണ് പ്രോബ്ലം? We have to apply more force. Okay, we have to apply more force. നിങ്ങൾ എക്സ്പീരിയൻസ് ചെയ്തിട്ടുണ്ടാവും ഒരു വാതില് തുറക്കുമ്പോഴോ അല്ലെങ്കിൽ ജനല തുറക്കുമ്പോഴോ we have to supply force at the extreme end, not at the hinge point. Hinge point load apply, maybe we are applying same force at the hinge point as well as in the extreme end, but the torque will be different. Maybe we are applying same force, but the torque is different. So torque is the product of force and the perpendicular distance from the rotating axis. Is the distance from perpendicular distance from rotating axis to the point of application of load. Okay, so that is the rotating force torque. So this perpendicular distance is an important factor when we considering a rotating member or rotating force. Okay, so that is the difference between the rotation axis and the point of application of load. That is torque or turning moment. So in such a rotating members, we are applying torque. Here we are applying torque. When we transmit the power, actually we are applying torque at the one end. Actually engine, in this case engine applying some amount of turning moment or torque onto the one end of the shaft. And this torque is actually transmitted from one point to next point. The rotating force is transmitted from one point to next point. Okay, so that is about torque. So what happened to the body when a body subjected to torque? For example, see this. See this. This is a shaft. Okay, so this shaft, for example, this end is connected with the wheel, and this end is connected with the engine. Okay, ഏതാണ് ആദ്യം സ്റ്റാർട്ട് ചെയ്യുന്നത്? എഞ്ചിൻ or wheel? Which one starts first? ഏതാദ്യം സ്റ്റാർട്ട് ചെയ്യുന്നത്? Engine is starting first. Right? So initially, when engine starts, we are applying actually a torque on the shaft. We are applying a torque on the shaft. But at the same time, at the starting time, the wheel is stationary. That means we can consider this end is fixed. Okay. So starting time, the wheel is stationary, or we can say this end is fixed, but this end is connected to engine. So when engine starts, we are applying a torque on this engine. We are applying a torque on this engine. So when I apply a torque on this engine, what happened? A twisting will occur. For example, in case of a rectangular shaft, we can see the twisting. A twisting will occur. See this twisting. This end is fixed. In this end, I am applying a torque. Okay, twisting. We can see a twisting. Initially, it was a rectangular cross section shaft, rectangular cross section, and this, if this end is fixed, and I am applying a force or rotating force or torque on this end, what happened? A rotation will be, or twisting will be developed on this shaft. Okay, so the shaft should have resist this twisting force or twisting deformation. When we apply external torque, this shaft should resist the twisting deformation. So how can we design a shaft to resist this twisting? So that is actually we are studying in this torsion area. Okay. So this is a member subjected to twisting, such a twisting force. Here we can see actually here I am applying just a rotating force. How this rotating force is applied? How this rotating force is applied? For that, just a second. For that, consider a lever. A lever is fixed in the end of this shaft. Okay, I am applying a force in this direction. In this direction, I am applying a force. A force is acting on this end, in this direction. Okay, and in the opposite direction, I am applying a normal force on this connecting member, in this member. Similar to this case, you can see. Sorry, so see this. Here we can see a rod is attached to this end of the shaft. Okay, I am applying a force in this direction. In this direction, I am applying a force which is normal to this connecting member. Okay, and at the bottom, I am applying in the opposite direction, the normal to this member. Okay, and applying a force in the bottom side. So this is almost similar to this case, right? This case. Okay, so when we apply a equal and opposite force on this connected member, what produce here? When I apply an equal and opposite force,
Couple.
a moment will be developed. What is the magnitude of that moment?
Force into perpendicular.
Yes, this force into the equal and opposite force is applied. This force into perpendicular distance. So that force into perpendicular distance is torque. Okay, that force into perpendicular distance is torque. So actually, I am actually at fix this point, and here actually I am rotating or applying torque. But the application of torque is like this: a force is applied in the equal and opposite direction, separated by a distance d. Then force into perpendicular distance d is called torque. So when I apply such torque, what happened to this body? What happened to this body? Here we can see in this figure. Here we can see in this figure. See, this is the body before deformation. This is the body before deformation. Okay. Here we can see some grid lines, and all the lines, these longitudinal lines are parallel to the axis before deformation. Okay, all the longitudinal lines are parallel to the axis. But here after deformation, what happened? After deformation, we can see these longitudinal lines, which is again parallel to the axis, but it is rotated by an angle. Initially, this longitudinal axis was straight. In this direction, it is straight. But after application of torque, what happened? This longitudinal axis rotate by an angle. We can see this longitudinal axis. Can you see this? Okay. This longitudinal axis rotate by an angle. Okay. Or a twisting is produced on this shaft. A twisting. See this. When I rotate this, initially we can see this face. This is a perfectly planar face. It's a planar face. So when I rotate, we can see it's not a plane. It's not a plane. So when we draw some longitudinal axis or longitudinal lines on the surface of this body, this longitudinal lines also will rotate with respect to this fixed point. Okay, so we can see this. If you draw 2 points here, I am drawing a point here. Here I am drawing a point here, and the same line I am drawing another point. This one. So we can see 2 points. Okay. So after rotation, we can see this not in the same line. It may be in same line, but this point is rotated by an angle with respect to this one. Okay. So that is twisting of the shaft when subjected to torque. Twisting of the shaft when subjected to torque. Any doubt? So we apply an external torque with based on this external torque, a twisting will occur on this shaft. Okay. So that is actually happen in this shaft. So this is a twisting. We can see this. So initially this is a rectangular plane pasted on a planar rectangular plane paper is pasted on the shaft. After twisting, we can see the shape of the paper. It's twisted. Okay, initially it was this edge was straight, but here we can see that is at an angle with the axis. Okay, so that is twisting. Here we can see this dark plane. Initially, this is the initial position, the dark plane. After deformation, we can see this dark plane shifted to this light plane. See this plane. Okay, this is the deformed plane. Is twisted by an angle phi of x. Okay, so this is twisting. So this is the figure of a shaft subjected to failure due to torsion. Okay, a shaft subjected to failure by torsion. So here we are going to analyze the shaft similar to what we studied in the first module. We are going to analyze this shaft. In this shaft, one end is fixed. This end is fixed. Okay. Okay. In this shaft, this end is fixed. This end of the shaft is fixed. And here I am applying a torque. A torque T is applied in this end. Okay. External torque T is applied. And here this end is fixed. There will be some resisting torque. Beam in the case, resistance and reactions and vertical forces in a reaction RA/RB. Similarly, when I apply a torque, external torque T here, a reaction torque will be developed with the same magnitude and opposite direction. Okay, a reaction torque will be developed on the fixed end. This is the fixed end. So this is the body which I am going to analyze. Here I am taking a plane. This is a plane. I am taking a plane at the center of this shaft. Okay, I am going to cut this shaft into two using this plane. Okay, using this plane, I cut this shaft into two. And this is the first half of the shaft, this half. Okay, I cut this body into two. I'm taking this area, this shaft for the analysis. So this is the shaft after cutting. Okay, this is shaft after cutting. So this is not, sorry, this end is taken for the analysis. This is the shaft. Okay, this is the shaft after cutting. So this is not, this one, sorry. This end is taken for the analysis. So this is the shaft after cutting. So this is not, this one, sorry. This end is taken for the analysis. So this is the shaft after cutting. So this is the shaft after cutting. So this end this end is taken for the analysis. Okay. So in this, if you take this plane, this cross section is shown here, this one, some resisting torque will be developed. Some resisting torque will be developed. Similar to the case of member subjected to axial load. Load enormous stress active correspondingly, if we take any cross section, at that cross section, some internal forces will be developed. Like resistance, internal forces will be developed. Similarly, to oppose this external torque at the cross section of that plane, a plane which cut the cross section, some internal torque will be developed in the opposite direction of the external torque. Actually, this internal torque resists the external torque without any twisting on the shaft. Without any twisting on the shaft, this internal torque resists external torque. Okay, so this internal torque is developed across any cross section of this shaft. Across any cross section of the shaft. So this is TR. I am calling this TR, that is the internal resistance developed similar to the internal force. We studied internal force. So stress is the amount of internal forces developed or resistance force developed across the unit area. That is stress. Similarly here, when we apply external torque, some internal torque is developed across any cross section of this shaft. Okay, that is TR. So next year, what is the reason for this internal torque? What is the reason for this internal torque? For example, here in this is a shaft. I fix this end of the shaft and applying a torque in this end. In this end, I am applying a torque. Okay, and this shaft is made up of 4 elements. You can see 4 elements is used to construct this shaft. Okay, so when I apply, so here this end is fixed. When I apply a external torque in this shaft, we can see some sliding. See this one sliding of one element with respect to another element. We can see some sliding. See this sliding. One element slide with respect to another element. Okay, what is the reason for this sliding? What type of force or stress is developed across that two sliding plane?
Shear stress.
Yes, shear stress is developed. Shear stress is developed because when we apply shear force, here we can see how this shear, for example, here in this end, I am applying a shear force. This is the direction of shear force applied. In this direction, I am applying a shear force. In the bottom direction also, I am applying the opposite direction, I am applying a shear force. What happened to this body? This body slide with one plane with respect to another, like this. So slide. So across this plane, a shear force is developed. A shear force is developed. The similar case is here. When external torque is applied in this body, this sliding is because of the shear force developed across these two planes. Or we can say, across every element of this body, a shear stress is developed or shear force is developed. So when we apply an external torque, across any cross section of the body, a shear stress is developed, not a normal stress. There is no normal stress developed, tensile or compressive. Only shear stress is developed. Okay, okay. So across this cross section, a shear stress is developed or a shear force is developed. This is very important. A member subjected to torsion, in every cross section, shear force is developed. Not any type of normal stress is developed across the cross section. Only shear force is the reason for the failure of the component due to torsion. Doubt undo karyathile? Any doubt? No. Okay. So we already discussed this. When I apply an external torque, some resisting torque will be developed. Internal resistance torque will be developed across any cross section. I am going to discuss the reason for this, how this internal resistance torque is developed. Okay, I am going to explain that, how this internal resistance torque is developed. For that, I am explaining this in this cross section. Every cross section of this or every element is subjected to shear force. So here we consider this cross section. In this cross section, I am taking this cross section. So this is that cross section, this cross section. In this cross section, some shear force is developed. So this is the shear force developed across the, sorry. So this is my cross section. In this cross section, some shear force is developed across this cross section. We already discussed how this shear force is. So across this cross section, some shear force is developed, and this shear force try to slide or slip one plane of element with respect to another plane of element. So this is the shear force. Across the cross section, such a shear force will be developed. Okay, these are the shear force. Any doubt? Okay, shear force F is developed across a cross section. If you take any cross section of the shaft. Okay, and this is the center of the shaft. Center of the shaft. For example, I am taking this shear force, this one. The distance from the center of the shaft to this shear force direction is equal to R. R is the distance from the center of the shaft to this shear force. Then what is the moment of this shear force with respect to center? What is the moment of this shear force F with respect to center? F into R, force into perpendicular distance. Moment is equal to force into distance. That is moment. So we can say this shear force make a moment with respect to center. And how can we calculate this moment with respect to center? By integral of, we have entire region, we have shear force. Everywhere we can see the shear force. Okay. So that is why I am going to integrate this. So integral of this shear force into R, force into distance, distance is moment. So integral of force into R, that is the total moment of this entire shear force with respect to center. Shariyano? In this cross section, we have number of such a shear force. Patayo. Hello? Okay. So in this cross section, there are such a number of such shear force, and each shear force at a distance R from the center. Okay. Each shear force make a movement with respect to center. That is force into radius. So the integral of force into this radius is the moment of all the shear force with respect to center. Okay. What is this integral force into radius? This is equal to what is this value? Integral of F into R. Yes, that is the resistant torque. That is the resistant torque developed internally when we apply an external torque. Okay, so this is the conclusion. When I am applying an external torque on the shaft, across any cross section of the shaft, an internal torque is developed. How this internal torque is developed? The internal torque is developed because of this shear stress or shear force developed across the cross section. And across any cross section, this shear force is developed. And shear force make a moment with respect to the center of the shaft. So the integral of the shear force moment with respect to the center is this resistant torque. That is the resistant torque. Any doubt?
Sir,
Yes.
integral over എന്താന്ന് പറഞ്ഞു
Integral the 0 to integral 0 to r.
Okay, sir.
That means from the center to the outer surface.
Okay.
Okay. And we will discuss more detail about this, but this is the concept. Integral 0 to r, f into r is the total moment of all the shear force with respect to center. This summation of all the moments with respect to center is the resistant torque developed across the cross section of the body or cross section of the shaft. This one, TR. Okay. Any doubt?
Okay, sir, no doubts.
Okay. So, a shear force, ഇത് നിങ്ങൾ മനസ്സിൽ വെച്ചിരിക്കണം കാരണം torsion member subjected to shear force. Shear force is developed across the cross section of the body when subjected to torsion. But beam member അല്ല എന്താ പറയുക നിങ്ങൾ പഠിപ്പിച്ചോ അതെ ബീമില് എന്ത് ഫോഴ്സ് ആ ഡെവലപ്പ് ചെയ്യുന്ന ഇതുപോലെ അത് പഠിപ്പിക്കുന്നുണ്ടാവുള്ളൂ ബീം മെമ്പർ bending force what type of force is it a normal or shear normal force ആണ് shear ബെൻഡിങ്ങില് സംഭവിക്കുന്നത് ബെൻഡിങ്ങില് രണ്ട് ഫോഴ്സ് ഉണ്ടാവും ബെൻഡിങ്ങില് രണ്ട് ഫോഴ്സ് ഉണ്ടാവും ഷിയർ ഫോഴ്സ് ഉണ്ടാവും നോർമൽ ഫോഴ്സ് ഉണ്ടാവും നോർമൽ മീൻസ് ടെൻസൈൽ ആൻഡ് കംപ്രസീവ് ബോത്ത് ടെൻസൈൽ ഉണ്ടാവും കംപ്രസീവ് ഉണ്ടാവും as well as shear force ഉണ്ടാവും but torsion member only subjected to shear force. Okay, so next I am explaining different terms associated with the torsion. Different terms associated with the torsion. The first one is shearing strain. So when this external torque is applied, some strain will be developed. The deformation can be measured in terms of strain as well as twist. We are using two terms for measuring the deformation here. The first one is shearing strain. So what is that? When I apply an external torque, I already explained this one. What happened to this straight lines? This line, if you take a particular line here, longitudinal line on the surface, it is twisted by an angle. We can see it is twisted by an angle. Okay. Similarly, here we can see a line. This AB line initially it was straight, is parallel to the AB axis of the shaft, but after applying a torque, it is shifted to AB dash. Okay, AB shifted to AB dash. And this angle between AB and AB dash is measured as shearing strain. Again, that is measured in radians. This angle, gamma, measured in radians is called shearing strain. Okay. And another one is angular twist. Angular twist is also another measure of deformation. So when this body is subjected to torsion, it is twisted by an angle. And if we measure this angle in the cross section, we can see the angle. Here we can measure an angle. Here we can measure an angle. Here, this angle is shearing strain. But if we measure the angle in the cross section, this angle is the angle of twist. How much is the one point is twisted with respect to another, with respect to the center of the cross section. That is angular twist. Okay, so this angle theta, we can see this angle theta, that is angular twist. But this angle of gamma in radian, that is the shearing strain. Any doubt? Any doubt? No? Okay. Another time we already discussed about that modulus of elasticity or shearing shear modulus, that is shear stress by shear strain. Okay, shear stress by shear strain. This is gamma, tau by gamma. That is modulus of rigidity. So all the string times is important for torsion. So this is the angular twist, and this is the, see this, initially this is after twisting. We can see the lines. A helical manner, in a helical manner, the lines on the surface is twisted. Okay, so this is the AB was the initial line before twisting. This is AB before twisting. After twisting, we can see A, B, A dash. This point will not change because this is the fixed end. There is no twisting at the fixed end, but at the free end, we can see the A point is shifted to AB dash, and this angle from A to center to A dash is called phi. That is the angular twist. And this angle is called, this angle is in radians is called shearing strain. Okay. So this is the before twisting, and this is a rectangular section after twisting. This is a circular section after twisting. Okay. And we will discuss some assumptions. So this is a member subjected twisting. So here we can see here a motor is connected, power is transmitted from motor to the another machine through this pulley and belt arrangement. Okay. So when we transfer the power from motor, what happened? A torque will be developed. A torque will be developed on the shaft. So across any cross section, shear force is developed, and the moment of the shear force is resisting torque developed across the cross section. Okay. So next we are going to derive a relationship between this applied torque and shear stress developed across the cross section. So here in this picture, we can say when we apply an external torque T, some shear force is developed or shear stress is developed across the cross section. Okay. Next, I am going to derive a relationship between the applied torque T, and I am applying a torque T. And when I apply a torque T across the cross section, a shear force or shear stress is developed. Shear stress is developed. What is the relationship between this T and the torque? So next, I am going to derive the relationship between this T and the torque. Okay. The next class, Abraham. Hello. Next class, Abraham.
Sir, 12:30, 12:29.
Lab ano?
അല്ല MOS.
MOF.
Sorry, MOS.
Okay. So here in this, so this cross section, shear force or shear stress is developed, and I am taking that cross section. In this picture, here we can see this end is fixed. This end is fixed. Here I am applying a torque T. Okay, a torque T is applied. When I apply a torque T, this a resistance will be offered by this fixed end. Okay, that is T, again T. This both are equal. Beam in the case beam vertical force apply support or a reaction of rate. So such type of reaction torque offered by this fixed end is T. Both are same. Okay, so here I am taking a cross section. This is the cross section. I am taking this cross section. I cut this body into two based on this cross section. Okay, in this cross section, a torque will be developed. Okay, a torque will be developed. Sorry, torque, no, it's not torque. A shear stress is developed. Torque or shear force is developed. This is the same cross section. This one is the same cross section. If you take the front view of that cross section, this will be the shear force direction or shear stress direction about the center. Okay, this is the along the cross section, along the plane of that cross section, shear force or shear stress is developed. Okay, so this is the shear stress, and we already discussed about complementary shear stress in the second module and first module. Complementary shear stress is developed. If we take a rectangle, and a shear stress is applied in these two faces, on the two other faces, some complementary shear stresses is developed to balance these two external shear stress. Similarly, if you take this rectangle on the surface of this shaft, here we can see a resistant torque is developed, resistance shear stress is developed. Here at this cross section also a shear stress is developed. If you take this cross section, a shear stress is developed here. If you cut along this cross section, a shear stress will be developed here. So two equal and opposite shear stress or shear force is developed. To balance these two shear force, a complementary shear stress is developed in the longitudinal direction. We can see a complementary shear stress is developed along the longitudinal direction, along the axial direction. This is in the lateral direction, this two shear force, but this two shear force or shear stress is along the longitudinal or axial direction. Okay, there is doubt undo? There is doubt illingi. My next question: if you take a wood member, I am constructing a shaft using a wood. Wood use the shaft to construct it. Okay, so when I applying an external torque, wood fail on the area. It's like longitudinal failure, not a cross section along the lateral failure, like this. The failure will be like this. What is the reason for that? What is the reason for that? Anyone? Wood is failed along the longitudinal axis when subjected to external torque, not along the lateral direction. What is the reason?
So because shear force is in the
Shear force?
in the longitudinal.
That is what type of shear force? We discuss here. There are two types of shear forces developed here. One is in the lateral direction. One is along the longitudinal direction. The longitudinal directional shear force is complementary shear force. Okay, actually, when we apply an external torque, actually these are the two shear forces. The lateral shear force is actually developed. But to balance this lateral shear force along the cross section, a complementary shear force is developed. These two are the complementary shear force. That complementary shear force direction is along the axis. Along the axis. So, what type of shear force is the reason for this type of failure?
Complementary.
Yes, complementary shear force is the reason for failure. Okay, but we can say this complementary shear force as well as this lateral shear force magnitude is same. Only direction is different. Magnitude is same. But magnitude same is lateral fail avande. Edondana longitudinal matram fail aaye. No, longitudinal matram fail aaye. The reason is this: in a wood particle, wood member the fibers in the wood is arranged like this. Fibers arranged in okay. So it is very easy to propagate crack in this direction. In the longitudinal direction, it is very easy to propagate the crack in the longitudinal direction, but it is very difficult to propagate the crack in the lateral direction because every fiber resists this lateral crack propagation. Okay. Both the stress in lateral as well as longitudinal or complementary shear stress and lateral shear stress is same. But if we take wood particles, the fibers arranged in the longitudinal direction, so it is very easy to propagate the crack in the longitudinal direction than that of the, even the forces and stresses in the both directions are same, but the direction, when we take the crack propagation direction, this direction, longitudinal direction is very easy compared to the lateral direction. That is why the wood is crack in this direction or fail in this direction. Okay. And this is the diagram showing the cross section. Here we can see this is this arrows. This is the direction of stress, shear stress, direction of shear stress along the cross section. Okay. And if you take a element from this cross section, this is the corresponding element. Or if you take this one, here we can see along the cross section some shear force is developed to resist the external torque. But this one, see this one, this lines, this is the complementary shear stress or shear force. Okay, these are the along the longitudinal direction some complementary shear stress is developed. Okay.
Sir, wooden shaft
വേറെ ഷാഫ്റ്റ് ആണെങ്കിൽ ഇപ്പൊ ഏതെങ്കിലും മെറ്റൽ ആണെങ്കിൽ ഇതായിരിക്കില്ല ഫെയിലിയർ. മെറ്റൽ ആണെങ്കിൽ ഫെയിലിയർ ആവുന്നത് ഇതുപോലെ ആയിരിക്കും, ട്വിസ്റ്റ് ഉണ്ടായിട്ട് ഇതുപോലെ ആയിരിക്കും, ക്രോസ് സെക്ഷനിലായിരിക്കും ഫെയിൽ ആവുക. കാരണം ക്രോസ് സെക്ഷനിൽ മെറ്റീരിയൽസ് കുറവാ, പക്ഷെ ലോഞ്ചിറ്റ്യൂഡ് ഡയറക്ഷനിൽ മെറ്റീരിയൽസ് കൂടുതലാണ്, അതുകൊണ്ട് ക്രോസ് സെക്ഷനിൽ ഫെയിൽ ആവും.
Okay, sir.
Okay. So next we are going to derive the relationship between torque and the externally applied torque and internally developed shear stress. Internally developed shear stress. What is the relationship between external torque and internally developed shear stress? Okay. So next I am going to explain that. അതങ്ങനെ കഴിയുമ്പോൾ ക്ലാസ് നിർത്താം. ഓക്കെ, പെട്ടെന്ന് തരും. For that, this is the shaft. A shaft subjected to external torque T. So this shaft is subjected to external torque T. One end of the shaft is fixed, one end is free. When I apply an external torque, there will be some twisting. So initially the point AB line, this is AB line on the surface. When I apply an external torque T, this B point shifted to B dash. Okay, B point shifted to B dash. And there is no change in the point A because this point A is fixed to the wall. So there is no change in the point A, but B shifted to B dash. And corresponding strain is equal to gamma. Already I explained. The shear strain is equal to gamma. And this theta value is the angular twist. L is the length of the shaft. Okay. And if you take the cross section, this is the cross section. The center is O. The center is O. Point B and B dash is marked here. This is point B and this is B dash. The angle between BO B dash is equal to theta. And the radius of the shaft is R. This is the front view. This one is the front view of the shaft. Any doubt? Okay. So in this, such a shaft okay, so here in this write this. So in this shaft, external torque applied is equal to T. T is the torque applied. The shear stress developed across that cross section is equal to tau. Shear stress, angular twist is equal to theta, shear strain is equal to gamma, length is equal to L, and the material made with the material modulus of rigidity of the material is equal to G. Okay, modulus of rigidity is equal to G. Okay, so in this figure, what is angle BAB dash? Angle BAB dash. BAB dash is equal to BAB dash. That is equal to gamma. Gamma. What is angle BOB dash? BOB dash. BOB dash. That is angular twist theta. Okay. Then take this BB dash arc. Take this BB dash arc. You can see this BB dash arc. What is the arc length BB dash? BB dash arc length is equal to, what is the value? Arc length is equal to, how can we calculate the arc length? For example, this is BB dash, this is the radius, this is theta. What is arc length?
R theta by 3.
BB dash is equal to R theta. Radius into angle, included angle is equal to arc length. Okay. So here, what is BB dash? In this figure, what is BB dash?
R theta.
That is equal to R theta. Again, what is BB dash arc length? So this arc BB dash belongs to this triangle as well as this. This is not a triangle. For this one, we can see for BAB dash, this BB dash is a part of B dash AB, and BB dash is a part of B dash OB. So again, we can write the arc length BB dash is equal to
Gamma L.
Gamma L. That is equal to gamma L. Gamma L. Okay. So take this. This is BB dash. Sorry, B dash B. B dash B. In this, this is equal to L. This is equal to L. This is equal to gamma. This is equal to gamma. And similarly, again, this is O. This is theta. So BB dash, this arc is equal to this radius is this is radius. So BB dash is equal to R theta. Again, BB dash is equal to gamma L, because this BB dash arc is common for this area and this area. Okay, so we can write both the BB dash arc length is equal to R theta and RL. From this we can write R theta is equal to gamma L. LHS is same. So R theta is equal to gamma L. From this we got gamma is equal to R theta by L. This is equation number 1. Gamma is equal to R theta by L. So this is the concept. This one is the concept. Both the arc length are same. Okay. What is G? What is G? Shear modulus is equal to, what's the value of G? What is E? G, K? What type of stress? Modulus or rigidity or shear modulus is equal to
Shear stress by shear strain.
shear stress by shear strain. Okay, from this shear strain is equal to tau by G in it. That is equation number 2. Shear stress by shear strain is equal to modulus of rigidity or shear modulus G. From this, gamma is equal to tau by G. So in equation number 1 and 2, both are gamma. So we can equate the right hand side. So r theta by L equal to tau by G. Okay. From this we can write tau by R is equal to G theta by L. Tau by R equal to G theta by the first equation. Okay, we got relationship between different parameters. That what is the different values? Tau is the shear stress developed across any cross section. R is the radius of the element where shear stress tau is acting. G is the modulus or rigidity of the material which is made for this shaft. Theta is the corresponding angular twist. L is the length of the shaft. Okay, L is the length of the shaft. So here in this we can see, in this equation we can see G is a constant. G is a constant. For a material, G will be a constant. Length will be also a constant. For a particular length shaft, L is also a constant. L will not vary. And this theta also is a constant value. Okay, theta is the angular twist. That is also a constant value. Because for a particular torque, there will be a theta. Okay. So we can write, from this we can write, tau is equal to all these terms, right hand side, all these terms are constant. So we can write a constant into R. Constant into R. Or we can write tau is proportional to R. Tau is proportional to R. Where what is the R? R is the, if you take a cross section, see, if I take this cross section, in this cross section, the shear force acting on every element, not on single element, everywhere shear stress is acting. Everywhere shear stress is acting. Everywhere on this cross section, even in the surface or interior portion, everywhere the shear stress is acting in the radial direction. Okay. So what is the R? R is not the cross section radius of the cross section. It is not this R. This R is not the cross section radius. The R is, if you take this element from this cross section, if we take this element from this cross section, okay, the distance from the center to that element, that is R. Okay, the distance from the center to that element is R. If you take a element here at the surface, and this is R, this is also another R. If you take another element here, this is also R. So R is the distance from the center to the element which we are considering to calculate this tau value. Okay, this tau value. So for a element, for example, in this I am taking this element, and into this element the radial distance is into the element is R. Then the shear stress tau developed on that element is equal to, this tau is nothing but the shear stress acting on that element. It is not on the surface or not on the interior, not on the center. It is this shear stress is the shear stress developed on the element which we are considering. That is at a distance R from the center. Okay, so that is T and tau and R. So this tau is proportional to R. Okay, this tau is proportional to R. Then next question, what is the what is the shear stress at the center? What is the shear stress at the center?
0.
Shear stress at the center is 0 because at the center, what is the value of R? If we consider an element at the center, what is the radius distance from the center to that element? It is equal to 0. If R equal to 0, then tau also equal to 0. Then, where is the location of maximum shear stress?
extreme and
At the extreme end of our surface. If we consider an element here, the radial distance is maximum at that element. Okay, so shear stress is maximum here, shear stress is minimum here. And we can say here tau is vary in a linear manner. This is not an R square or R cube, etc. This is single R raised to 1. So that means with respect to R, tau is varying in a linear direction. This is the variation of tau. I am drawing the variation of tau. Here it will be 0. And the tau value increase from 0 to maximum value when it is approached to surface. So this is the variation of tau. Shear stress is 0 at the center of the shaft, maximum at the surface. Maximum at the surface. Any doubt?
Sir,
Yes.
theta എങ്ങനെയാ constant ആയെന്ന് പറഞ്ഞു തരാം.
For a particular torque, ഒരു particular torque നമ്മൾ അപ്ലൈ ചെയ്യുമ്പോൾ അതിനൊരു സ്പെസിഫിക് ആയിട്ടുള്ള തീറ്റ ഉണ്ടാവുള്ളൂ. ഒരു കോൺസ്റ്റന്റ് ടോർക്ക്.
അപ്പൊ ടോം കോൺസ്റ്റന്റ് ആയില്ലേ?
അല്ലല്ല, ഞാൻ കേക്ക്. ഒരു ക്രോസ് സെക്ഷൻ എടുക്കുമ്പോ, ഇപ്പൊ ഈ ഒരു ക്രോസ് സെക്ഷൻ എടുക്കുമ്പോ അതിലൊരു സിംഗിൾ തീറ്റ ഉണ്ടാവുള്ളൂ. ആംഗുലർ ട്വിസ്റ്റ് ഒരു ക്രോസ് സെക്ഷനില്, ഞാൻ ഒരു ക്രോസ് സെക്ഷനിലുള്ള കാര്യം പറയുന്നത് ഇതെല്ലാം. ഒരു ക്രോസ് സെക്ഷനില് തീറ്റ എന്ന് പറഞ്ഞ സിംഗിൾ വാല്യൂ ആയിരിക്കും. അതിന് ഫോർ എക്സാമ്പിൾ ഈ ഒരു കേസില് ഇപ്പൊ ഇവിടെ ഈ ഒരു ക്രോസ് സെക്ഷനില് ഇപ്പൊ ഞാൻ ഇവിടെ ഒരു തീറ്റ എടുത്താലും തീറ്റയ്ക്ക് വ്യത്യാസം ഉണ്ടോ? അല്ല ഇവിടെ തീറ്റ എടുത്താൽ തീറ്റയ്ക്ക് വ്യത്യാസം ഉണ്ടോ? ഏത് പോയിന്റ് എടുത്താലും തീറ്റ സിംഗിൾ വാല്യൂ ആണ്. ഒരു ക്രോസ് സെക്ഷനിൽ ഞാൻ ഇങ്ങനെ വേരി ചെയ്താ ഈ പോയിന്റിൽ നിന്ന് ഇങ്ങോട്ട് വേരി ചെയ്യാണ്, തീറ്റയ്ക്ക് വ്യത്യാസം ഉണ്ടോ? everywhere theta is same. Okay.
പക്ഷെ for a particular value of tau എന്നല്ലേ? അപ്പൊ
അല്ലല്ല, particular value of tau അല്ല. particular value of tau അല്ല. If you take a cross section, ഒരു ക്രോസ് സെക്ഷൻ എടുത്തു കഴിഞ്ഞാൽ ആ ക്രോസ് സെക്ഷനില് സിംഗിൾ തീറ്റ ഉണ്ടാവുള്ളൂ. ആ ക്രോസ് സെക്ഷൻ ഇപ്പൊ ആ ഒരു വേറെ ഫിഗർ കാണിച്ചു തരാം, അപ്പൊ കുറച്ചും കൂടി ക്ലിയർ ആവും. ഇപ്പൊ ഈ ഫിഗർ എടുത്തു വെച്ചോ. ഈ ഫിഗറിൽ ഒരു ക്രോസ് സെക്ഷൻ ഞാൻ കൺസിഡർ ചെയ്യാണ്. ഈ ഒരു ക്രോസ് സെക്ഷൻ കൺസിഡർ ചെയ്യുമ്പോൾ അവിടെ എത്ര ആംഗുലർ ട്വിസ്റ്റ് ഉണ്ടാവും? ആ ഒരു ക്രോസ് സെക്ഷൻ കൺസിഡർ ചെയ്യുമ്പോൾ ഒറ്റ സിംഗിൾ തീറ്റയിൽ ഉണ്ടാവുള്ളൂ. ഈ ഒരു ക്രോസ് സെക്ഷൻ കൺസിഡർ ചെയ്ത് കഴിഞ്ഞാൽ അവിടെ ഏത് ലൈൻ വരച്ചു നിങ്ങള്? ഇപ്പൊ ഈ ലൈൻ വരെ ഞാൻ വേറെ ലൈൻ വരയ്ക്കുകയാണ്. ഫോർ എക്സാമ്പിൾ ഇനിഷ്യൽ ലൈൻ ഇതായിരുന്നു. അതൊരു വെർട്ടിക്കൽ ആംഗിളിൽ ട്വിസ്റ്റ് ചെയ്തത് ഇങ്ങോട്ടായി. ഇത് ബിറ്റ്വീൻ ആയിട്ടുള്ള ഒരു ആംഗിൾ തീറ്റ എടുത്തു. ഈ തീറ്റയും സെയിം ആയിരിക്കും. കാരണം എന്താ? ഇത് രണ്ടും ട്വിസ്റ്റ് ചെയ്യുന്ന സെയിം എമൗണ്ടാ. ഒരു ക്രോസ് ട്വിസ്റ്റ് ചെയ്യുന്ന സെയിം എമൗണ്ടാ. മനസ്സിലായോ? അപ്പൊ തീറ്റ ഒരു ക്രോസ് സെക്ഷൻ എടുക്കുമ്പോൾ സെയിം ആയിരിക്കും. ബട്ട് ഞാൻ വേറൊരു ക്രോസ് സെക്ഷൻ എടുക്കാന്ന് വെച്ചാൽ ഇതിന് പകരം വേറെ ക്രോസ് സെക്ഷൻ എടുത്താൽ അത് ഡിഫറെന്റ് ആയിരിക്കും. ഞാൻ പക്ഷെ ഈ ഫോർമുല പറയുന്ന ഒരു ക്രോസ് സെക്ഷനിലെ കാര്യം പറയുന്നത്. ഈ ക്രോസ് സെക്ഷനില് എന്താ പറയാ, നമ്മുടെ ടോയും വേരി ചെയ്യുന്നത് വിത്ത് റെസ്പെക്ട് ടു ആർ ഉള്ളു. അതിൽ ഈ ജി എന്ന് പറയുന്നത് തീറ്റായും എല്ലാം ഒരു ഫാക്ടർ അല്ല. So at the center it is 0, at the surface it is maximum. From the center to surface it is varying in a linear direction. Okay. My next question is this. ഇപ്പൊ തന്നെ ചോദിക്കാമോ അറിയില്ല, എങ്കിലും ആരെങ്കിലും ആൻസർ പറയുന്നോട്ടെ. which one is better for power transmission? Hollow shaft or solid shaft? Hollow shaft or solid shaft? Which one is good for power transmission? For example, consider two shafts with the same weight. One with the hollow, one with the solid. Which one is good for power transmission? Which one has higher strength? Hmm?
Solid.
What is the reason for that? The reason?
The maximum power എന്തായാലും extreme ഇതിലല്ലേ വരുള്ളൂ.
Yes. Maximum stress develop ചെയ്യും. നമ്മളെപ്പോഴാ ഒരു ബോഡിയുടെ ഇത് വരിക? ഫോർ എക്സാമ്പിൾ ഒരു ഷാഫ്റ്റ് എപ്പോഴാ ഫെയിൽ ആവുന്നത്? ഇങ്ങനെ ക്രോസ് സെക്ഷനിൽ ഡെവലപ്പ് ചെയ്ത ഒരു ക്രോസ് സെക്ഷനിൽ ഡെവലപ്പ് ചെയ്യുന്ന ഷിയർ സ്ട്രെസ് ആ മെറ്റീരിയലിന് ഒരു അലോബിൾ ഷിയർ സ്ട്രെസ് ഉണ്ടാവും അല്ലേ? നമ്മൾ നേരത്തെ പറഞ്ഞ ആ മെറ്റീരിയലിന് ഒരു അലോബിൾ ഷിയർ സ്ട്രെസ് ഉണ്ടാവും. ആ മെറ്റീരിയലിന്റെ അലോബിൾ സ്ട്രെസ്സിനേക്കാൾ കൂടുതലാണ് ഈ ക്രോസ് സെക്ഷനിൽ ഡെവലപ്പ് ചെയ്ത ഷിയർ സ്ട്രെസ് എങ്കിൽ ആ ഷാഫ്റ്റ് ഫെയിൽ ആവും അല്ലെ? അങ്ങനെയല്ലേ നമ്മൾ പഠിച്ചതാണ് മറ്റേ ഇതിന്റെ കേസിലെല്ലാം. ഒരു മെറ്റീരിയലിന്റെ അലോബിൾ ഷിയർ സ്ട്രെസ് അല്ലെങ്കിൽ അലോബിൾ സ്ട്രെസ് ഉണ്ടാവും. അതിനേക്കാൾ കൂടുതലാണ് അതിന്റെ ക്രോസ് സെക്ഷനിൽ ഡെവലപ്പ് ചെയ്ത ഷിയർ സ്ട്രെസ് എങ്കിൽ. ഞാൻ എക്സ്റ്റേണൽ ടോർക്ക് അപ്ലൈ ചെയ്തപ്പോ അതിന്റെ ക്രോസ് സെക്ഷനിൽ ഡെവലപ്പ് ചെയ്ത ഷിയർ സ്ട്രെസ് ആ മെറ്റീരിയലിന്റെ അലോബിൾ ഷിയർ സ്ട്രെസ് ഹയർ ആയി കഴിഞ്ഞാൽ മെറ്റീരിയൽ ഫെയിൽ ആവും. അപ്പൊ എന്താ നമ്മൾ ചെയ്യേണ്ടത്? ഈ ഡെവലപ്പ് ചെയ്ത ഷിയർ സ്ട്രെസ് മിനിമം ആക്കുക അല്ലേ? ഈ ഡെവലപ്പ് ചെയ്യുന്ന ഷിയർ സ്ട്രെസ് മിനിമം ആക്കും തോറും അല്ലെങ്കിൽ അതിനെ റെഡ്യൂസ് ചെയ്യും തോറും ദ സ്ട്രെങ്ത് ഓൾസോ ഇൻക്രീസ്ഡ്. ഹൗ ക്യാൻ വി ഇൻക്രീസ് ദ സ്ട്രെങ്ത്? By reducing this developed shear stress. How can we reduce the shear stress value? By adding more material on the surface. The surface area is the region of higher shear stress value. So if we add more material on the surface, we can reduce the shear stress value on the surface. How can we add more material? By taking material from the center region. This is the region of minimal shear stress. So we can take the material from the center region and we can distribute that material into the outer surface region. Okay, so we take the material from the region of lower shear stress and we distribute that material into the region of higher shear stress. Thereby we can reduce this shear stress develop across the cross section. മനസ്സിലായോ?
സർ അപ്പൊ ഹോളോ ആണോ നല്ലത്?
Yes, hollow shaft is better than with the same weight. If you consider two shafts, one is solid and another one is hollow, with the same weight, for power transmission, hollow shaft is better than that of solid shaft because there is no need of material in the center region. Because already the stress developed in the center region is very small. Okay, so we can take the material from the center region and we can distribute the same material in the outer region. That is hollow shaft. Okay, that is the hollow shaft.
സർ അപ്പൊ ഫീൽ ആയിട്ട് കാണിച്ചൊരു ബീം ഉണ്ടായില്ലേ, അത് ഹോളോ ആയിരുന്നല്ലേ? സർ ആദ്യം പ്രസന്റ് ചെയ്ത ഒരു പടം ഫെയിൽ ആയിട്ട് കാണിച്ചതൊരെണ്ണം.
ഫെയിൽ ആവാം. ഞാൻ എല്ലാ ഹോളോ ഷാഫ്റ്റും ഫെയിൽ ആവാൻ പറ്റില്ല എന്ന് ഞാൻ പറയണില്ല. അതിന്റെ ബട്ട് ഞാൻ പറഞ്ഞല്ലോ സെയിം വെയിറ്റ് ആണെങ്കിൽ ഒരു സോളിഡ് ഷാഫ്റ്റും ഒരു ഹോളോ ഷാഫ്റ്റും വിത്ത് സെയിം വെയിറ്റ്, രണ്ടിനും സെയിം വെയിറ്റ് ആണെങ്കിൽ ഹോളോ ഷാഫ്റ്റ് ഈസ് ബെറ്റർ ദാൻ ദാറ്റ് ഓഫ് സോളിഡ് ഷാഫ്റ്റ്. എല്ലാ ഹോളോ ഷാഫ്റ്റും സ്ട്രോങ് ആണല്ല ഞാൻ പറഞ്ഞു. When we compare a solid shaft and a hollow shaft with the same weight, then hollow shaft is stronger than that of solid shaft.
Okay, sir.
Okay, so this is the reason. And അതിനെ കുറിച്ച് കൂടുതൽ ഞാൻ പിന്നീട് എക്സ്പ്ലെയിൻ ചെയ്യുന്നുണ്ട്. നിങ്ങൾക്ക് 12:30-ക്കാണോ ക്ലാസ് തുടങ്ങുന്നത്? MOF 12:30-ക്കാണോ? Okay, എന്നാ പിന്നെ ഫിനിഷ് ചെയ്യാം. So this is the distribution. ഇതുണ്ടോ? ഡിസ്ട്രിബ്യൂഷൻ ഉണ്ടോ? See the distribution of shear stress. Maximum shear stress is at the surface, minimum at the center region. Okay. Another figure, this one. See this figure. Here we can see at the center region it is 0 and shear stress is increased to maximum value at the surface. And in here we take an element here, and in that element, this is the shear stress across the plane of cross section. This one. This one is the, I mean, if you take this one, this is the shear stress across the plane of cross section. Similarly, on the opposite plane, same plane with the opposite cross section, we can see the same downward direction shear stress. And this top, the horizontal one, along the axial direction, this is the complementary shear stress, this one, and the bottom, this one. Okay, so if you take an element, there will be 4 shear stress value. One is along this plane, this one along this plane. If you take another cross section here, the opposite side of this element, another cross section, in that a downward direction shear stress will be developed, and a complementary shear stress develop on this horizontal direction on the top and the bottom of the element. Okay, so such a 4 shear stress value will be developed. This is important. This complementary shear stress, the magnitude, this cross-sectionally developing the shear stress in the magnitude is same. Okay. Next class, actually, derivation or continuation. I പറഞ്ഞ സംഭവം തീർക്കായിരുന്നു. ഈ പറഞ്ഞ കാര്യം ഞാൻ ഒരു 10 മിനിറ്റ് കൂടി എടുത്തോട്ടെ, 10 minutes, അല്ലെങ്കിൽ നിങ്ങൾക്ക് കണ്ടിന്യൂഷൻ കിട്ടില്ല. 10 minutes. ഇപ്പൊ 11:55 അല്ലേ ഉള്ളൂ. എടുക്കട്ടെ? Okay, so next I am going to derive. So here this is only the relationship between tau and r, and some more constant values are there. Okay, so if we consider a plane, the relationship between the shear stress developed and the distance from the center to the element consider, center to the element consider. Okay, so this relationship gives that relation between tau and r, the relation between the shear stress developed across any element and the distance from the center to the element is this relationship. So this is the A. Equation number A. I am deriving next equation, equation number B, that gives the relationship between T and tau. Here in this equation there is no term tau or the term illa. Applied torque in the term illa. Develop the shear stress, radius, angular distance, length, modulus rigidity relation. Next I am going to derive the relationship between T and tau. Okay, for that I considering a circular cross section. In that cross section, I am considering a small elemental area. This red one is a small elemental area with the thickness of dx. Dx is the thickness. Small elemental area with the in the cross section of the shaft. Okay, this is not a hollow shaft. This is a solid shaft, and in that solid shaft, I take a elemental area with the thickness to dx. That is at a distance x from the center. Okay, and the radius of the shaft is cross section radius is equal to r. Okay, this is not the distance to the element, it is the radius of the shaft r. Okay, and here in this at this radius, if I consider an element where shear stress developed is equal to tau. Tau is the shear stress developed. Okay. And in this, at this element, a shear stress of tau x is developed. Here, shear stress is different because we can see the distance from the center to this point, that is x, but from the center to this point is r. Okay, so here, so we already derived the tau is proportional to the distance from the center to that element. Okay, so here from the center to this element is r, where shear stress is tau, but here from the center to this element, this point, that is x, where shear stress is tau x. Okay, so I can write that tau by r equal to tau x by x. In എഴുതാൻ പറ്റുമോ? Tau by r equal to tau x by x. ശരിയല്ലേ? The tau is proportional to r. So ഈ tau എന്ന് പറയുന്ന ഇവിടെ സർഫസിൽ ഉള്ള tau, that is a maximum torque. Sorry, maximum shear stress. Maximum shear stress ന് corresponding ആയിട്ടുള്ള radius of the shaft, that is r. So tau by r, that is equal to ഈ പോയിന്റിലുള്ള shear stress എന്ന് പറഞ്ഞ tau x. Tau x അതിലേക്കുള്ള distance x. So we can write tau by r equal to tau x by x. Doubt undo? So from this, tau x equal to, we can write tau by r into x. Okay. And next, area of this element. What is the area of this element? The red hashed element. Area of the element dA equal to, what is the area of the element? Is perimeter into thickness. That is the area. And the perimeter is 2 pi x. 2 pi r ഒരു സർക്കിൾ ഉണ്ട്. അപ്പൊ ഇവിടെ r ന് വരെ x ആണ്. അപ്പൊ ഈ ഇതിന്റെ പെരിമീറ്റർ എന്ന് പറഞ്ഞാൽ 2 pi x into thickness എന്ന് പറഞ്ഞാൽ dx ആണ്. So into dx. That is the area. 2 pi x into dx. Doubt illalo? 2 pi x into dx is the area of this, the red hashed elemental area. And the area കിട്ടി. ആ ഏരിയയിൽ ആക്ട് ചെയ്യുന്ന ഷിയർ സ്ട്രെസിന്റെ വാല്യൂ കിട്ടി tau x. What is the value of shear force? Shear force is equal to shear stress into ഈ ഏരിയയിൽ ആക്ട് ചെയ്യുന്ന ഷിയർ ഫോഴ്സിന്റെ വാല്യൂ കാൽക്കുലേറ്റ് ചെയ്യാൻ പോകുന്നത്. Shear force is equal to shear stress into area. So that is into dA. This dA. Okay. That is shear force. Already we derived the tau x value. So this is equal to tau by r into x into, that is tau x. Tau x. What is the value of dA? dA is equal to 2 pi x into dx. 2 pi x into dx. From this we can write shear force is equal to, so shear force is equal to stress is equal to force by area. അതുകൊണ്ടാണ് shear force is equal to stress into area എന്ന് എഴുതിയത്. Okay, so shear force is equal to tau by r into x square, x into x into x square into 2 pi into dx. From this I can write 2 pi by r into tau into x square dx is the shear force. Rearrange ചെയ്തു. That is the shear force value. Okay, shear force developed. Any doubt? Any doubt? അപ്പൊ ഈ പോയിന്റിൽ അല്ലെങ്കിൽ ഈ എലമെന്റൽ ഏരിയയിൽ ആക്ട് ചെയ്യുന്ന ഷിയർ ഫോഴ്സിന്റെ വാല്യൂ കിട്ടി. ഞാൻ ഈ tau x ന് വരെ ഞാൻ ഇനി F എന്ന് എഴുതുവാണ്. അവിടെ ആക്ട് ചെയ്യുന്ന ഷിയർ ഫോഴ്സ്, ഷിയർ സ്ട്രെസ് മാറ്റി ഷിയർ ഫോഴ്സ് ആക്കി. ഷിയർ ഫോഴ്സ് ഇങ്ങനെ ആക്ട് ചെയ്യുകയാണ് ഈ എലമെന്റിന്റെ ഏരിയയിൽ. ഓക്കെ, ഇനി നെക്സ്റ്റ് ക്വസ്റ്റ്യൻ ഇതാണ്. വാട്ട് ഈസ് ദ മൊമെന്റ് ഓഫ് ദിസ് ഫോഴ്സ് വിത്ത് റെസ്പെക്ട് ടു സെന്റർ? മൊമെന്റ് ഓഫ് ദിസ് ഫോഴ്സ്, ടേണിംഗ് മൊമെന്റ് ഓഫ് ദിസ് ഷിയർ ഫോഴ്സ് വിത്ത് റെസ്പെക്ട് ടു സെന്റർ. നമ്മൾ നേരത്തെ പറഞ്ഞു ഓർക്കണ്ടോ? ഈ ഷിയർ ഫോഴ്സ് സെന്ററുമായിട്ട് ഒരു മൊമെന്റ് ഉണ്ടാക്കും. അത് എത്രയാ?
shear force into radius.
റേഡിയസ് ഓർ എക്സ് അല്ലേ?
And the concrete cross section.
അല്ലേ? സോ ഷിയർ ഫോഴ്സ് ഇൻറ്റു പെർപെൻഡിക്കുലർ ഡിസ്റ്റൻസ് എന്ന് പറഞ്ഞാൽ എക്സ് ആണ് ഇവിടെ. ഈ ഷിയർ ഫോഴ്സിൽ നിന്ന് ഇതിലേക്കുള്ള ഡിസ്റ്റൻസ് എക്സ് ആണ്. സോ എഫ് ഇൻറ്റു എക്സ്. സോ ഐ ആം റൈറ്റിംഗ് ദ മൂമെന്റ് ഓഫ് ടേണിംഗ് മൊമെന്റ് എന്ന് എഴുതാം. ടേണിംഗ് മൊമെന്റ് ഓഫ് എഫ് വിത്ത് റെസ്പെക്ട് ടു turning moment of F shear force with respect to center is equal to F into X. We already calculate the value of F. Here F is equal to 2 pi by R into tau into X square into dx into X. X on it. This is F. So we can write 2 pi by R into tau into X square into x cube into dx. X cube into dx. X cube into dx. That is the turning moment of that force. ഈ ഫോഴ്സ് ഉണ്ടാക്കുന്ന ടേണിംഗ് മൊമെന്റ് ആണ് കിട്ടിയത് ഈ ഫോഴ്സ്. അപ്പൊ ഇതുപോലെ നമ്പർ ഓഫ് ഫോഴ്സസ് ഉണ്ടാവും ഈ ക്രോസ് സെക്ഷനിൽ. ഷിയർ ഫോഴ്സ്, നമ്പർ ഓഫ് ഷിയർ ഫോഴ്സസ് ഉണ്ടാവും. അതിന്റെ എല്ലാത്തിന്റെയും ടേണിംഗ് മൊമെന്റ് എങ്ങനെ കാണും? ഇന്റഗ്രേറ്റ് ചെയ്യാം. സോ ടേണിംഗ് മൊമെന്റ് ഓഫ് all forces about center equal to integral of what is the range? 0 to r. അതല്ലേ റേഡിയസ് അല്ലേ? ഇവിടെ മുതൽ ഇവിടെ വരെ വന്നെങ്കിൽ all forces from the center to surface. അപ്പൊ ഇന്റഗ്രലിന്റെ റേഞ്ച് 0 to r. സോ ഇന്റഗ്രൽ 0 to r. അഗൈൻ ഇത് ഒരു സിംഗിൾ ഫോഴ്സിന്റെ. അപ്പൊ ഓൾ ഫോഴ്സസിന്റെ വരുമ്പോൾ ഇതിന് ഇന്റഗ്രേറ്റ് ചെയ്യണം വിത്ത് റെസ്പെക്ട് ടു r. സോ റൈറ്റ് ദിസ് 2 pi by r into tau into x cube into dx, where these terms are constant with respect to ഇവിടെ വേരിയബിൾ ആയത് x ആ. x is the variable. So 2 pi by r into tau, the integral 0 to r x cube into dx, variable x ആ ഇവിടെ. Okay, so from this we got 2 pi by r into tau into x cube in the integral x raised to 4 by 4 in the range of 0 to r. So from this we got 2 pi by r into tau r raised to 4, like this is equal to r raised to 4 by 4. R raised to x is replaced with the r. Integrate the range apply though. R raised to 4 minus 0 raised to 4. That is equal to r raised to 4. Now r ne ഞാൻ വേറൊരു ടൈമിലേക്ക് ആക്കുവാണ്. r നെ d യുടെ ടൈമിലേക്ക് ആക്കുവാണ്. That is equal to d യുടെ ടൈമിലേക്ക് ആക്കുമ്പോൾ 2 pi by r into tau into r is equal to d by 2. So r is equal to d by 2. So അത് വരുമ്പോൾ എന്ത് വരും? d by 2 whole raised to 4 by 4. Okay, from this we got, by rearranging, we got tau by r into pi d raised to 4 by 32. So we got this equation, tau by r into pi d raised to 4 by 32. And what is this left hand side? Turning moment of all forces about the center. Turning moment of all shear force about the center. What is that? നമ്മൾ ആദ്യം ഡിസ്കസ് ചെയ്ത സാധനം ഉണ്ടോ? ഈ ഷിയർ ഫോഴ്സ് എല്ലാം വിത്ത് റെസ്പെക്ട് ടു സെന്റർ ഉണ്ടാക്കുന്ന ടേണിംഗ് മൊമെന്റ് എന്ന് പറയുന്നതാണ് ഇന്റേണൽ റെസിസ്റ്റൻസ് ടോർക്ക്. ദാറ്റ് ഇന്റേണൽ റെസിസ്റ്റൻസ് ടോർക്ക് ഈസ് ഈക്വൽ ടു ദ എക്സ്റ്റേണൽ റെസിസ്റ്റൻസ് ടോർക്ക്. അതുകൊണ്ട് എന്ത് എഴുതാം? ഇതിന് ലെഫ്റ്റ് ഹാൻഡ് സൈഡിൽ എന്ത് എഴുതാം? എനിക്ക് ഇതിന് വേറെ എന്ത് എഴുതാം? അതിന് വേറെ എന്ത് എഴുതാം?
ടോർക്ക്.
യെസ്, ടി എന്ന് എഴുതാം. ടോർക്ക്. സോ ദിസ് ഈസ് ഈക്വൽ ടു ടി ഈസ് ഈക്വൽ ടു tau by r into pi d raised to 4 by 32, where pi d raised to 4 by 32 is called polar moment of inertia J. It's collectively called polar moment of inertia J. From this we got P by J is equal to tau by r. This is the second equation. P by J is equal to tau by r. So relationship between torque and shear stress develop across the cross section. അപ്പൊ ഇത്രയും പോർഷൻസ് ഞാൻ നിങ്ങൾക്ക് നോട്ട്സ് സെൻഡ് ചെയ്തേക്കാം, ടെക്സ്റ്റ് ബുക്ക് വായിക്കാം. അപ്പോ ഇതിനെ കുറിച്ച് ഇത്രയും പോർഷൻസിനെ കുറിച്ചുള്ള ഡൗട്ട്സ് നിങ്ങളുടെ ഹിബ്ലറിന്റെ ടെക്സ്റ്റ് ബുക്ക് നിങ്ങൾ വായിച്ചു കഴിഞ്ഞാൽ ഈ ഫിഗേഴ്സ് വെച്ച് എല്ലാം നല്ല ഐഡിയാസ് കിട്ടും. ഹിബ്ലറിന്റെ ടെക്സ്റ്റ് ബുക്ക് അതില് പ്രോപ്പർ ആയിട്ട് ഇതിന്റെ എല്ലാം കൺസെപ്റ്റ് വൈസ് കൊടുത്തിട്ടുണ്ട് ഹിബ്ലറിന്റെ ടെക്സ്റ്റ് ബുക്ക്. ഞാൻ റെഫർ ചെയ്ത ടെക്സ്റ്റ് ബുക്ക് അതാണ്, അത് നിങ്ങൾ റെഫർ ചെയ്താൽ മതി. ഓക്കെ, ഹിബ്ലറിന്റെ ടെക്സ്റ്റ് ബുക്ക് എടുത്ത് ടോർഷൻ, അപ്പൊ കൺസെപ്റ്റ് വൈസ് എല്ലാ പിക്ചർ ആയിട്ട് നല്ല രീതിയിൽ കൊടുത്തിട്ടുണ്ട് ഹിബ്ലറിന്റെ ടെക്സ്റ്റ് ബുക്കിൽ കേട്ടോ. അപ്പൊ അതും എന്റെ നോട്ടും വെച്ചിട്ട് പഠിക്കുക. ഇതിൽ ഇഷ്ടം പോലെ പ്രോബ്ലംസും ഉണ്ട്, ഇഷ്ടം പോലെ പ്രാക്ടിക്കൽ പ്രോബ്ലംസും ഹിബ്ലറിന്റെ ടെക്സ്റ്റ് ബുക്ക് ഉണ്ട്, അത് പഠിക്കുക. ഇതുവരെയുള്ള 2 ഫോർമുലാസിന്റെ ഡെറിവേഷനും പഠിക്കണം, ഇതിന്റെ കൺസെപ്റ്റ്സും പഠിച്ച് നെക്സ്റ്റ് ക്ലാസ്സിൽ വരിക കേട്ടോ. ഓക്കെ,
ഓക്കെ സർ.
ഒന്ന് ലീവ് ചെയ്തോ. ഓക്കെ, താങ്ക് യു.
Thank you, sir.
Thank you.
താങ്ക് യു.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir. Thank you, sir.